So last day we were looking at situations where we were already at equilibrium and we were calculating the KEQ, or we were using the KEQ to calculate an equilibrium concentration. Today, we're going to be looking at situations where we are not yet at equilibrium. Okay, so we're not there yet. And this is going to involve the use of these lovely things called rice tables. Rice tables, I'm going to say you guys are going to get a toolkit over the next little while. One of the tools you already have, it is your KEQ expression. This is the next tool you're going to get. It is a rice table. And so every time you do a question, you're going to think, which things do I need to pull out of my toolkit when you're doing a mathematical question? So the I stands for initial, the E stands for equilibrium, and the C stands for change in. So we are looking at systems where we initially start with either only reactant present or only product present. If that's the case, if we have only reactant or only product, are we at equilibrium? No. Okay. So the system will need to then shift. And if you recall, shifts are always proportional to the coefficients, and that will come in handy today when we actually start doing the math. So here is a situation. Our reaction, we've got SO2 and O2. Those are our reactants, and our product is SO3. So on the graph on the left, we are starting with some amount of reactants, and the products are starting at 0. So we have reactants only. And eventually we reach equilibrium, everything shifts. In the situation on the right-hand side, we are starting with SO3, which is the product. So we're starting with products only. And the reactants are starting at 0. And over time, again, an equilibrium is reached. But let's take a look at where these end up. SO3, our product, ends up here. And if we go across, ooh, look, SO3 ends up in the same place. SO2, same thing. If we follow it across, SO2 ends up in the same place. I didn't do a very good job of drawing that one. And O2 also ends up in the same place because KEQ, which is the concentration of products over the concentration of the reactants, concentration of products over concentration of reactants, these two are the same. You get the same number. No matter what you start with. Okay, so KEQ is always the same at a given temperature, no matter what you start with. Okay, so we have an example coming up here where we've got 2 NOCl in equilibrium with 2 NO and 1 Cl2. Those are all gases. And we are told that initially 2 moles of NOCl was placed in a 1 liter flask at 462 degrees Celsius, and it was left to reach equilibrium. So was this system at equilibrium to start with? No. Okay, so this language here tells you we were not at equilibrium to start with. When equilibrium is established, this is another thing that tells us we were not at equilibrium to start with. It was found that 0.66 moles of NO were present. Calculate the KEQ. Well, what we're going to do is we're going to say, okay, this quantity here, this 2 moles of NOCl in 1 liter, that is an initial quantity. And we're going to set up our rice table. And in our first row of the rice table, that stands for the reaction. And then we have our initial concentration, the change in concentration, and the change in concentration represents the shift. And finally, we have our equilibrium concentration. So that is a rice table. And what we can do, it's not always necessary. You don't have to draw these lines, but I find it sometimes it makes it a little easier. And we're going to fill in anything we can find from the question. So if we know an initial concentration, we're going to put it in. If we know an equilibrium concentration, we're going to put it in. And then we solve the rest of them like a little puzzle. So let's see, what do we know? We know that there were 2 moles of NOCl in 1 liter, and that was initially. So that is 2 molar. Because the math is so easy on that one, 2 divided by 1, I'm not going to make you show the calculation. So we're going to put this in here, 2.00. Now, this does have a unit. Okay, this is molar, but you don't need to write molar because we are dealing with KEQ, and KEQ has no units. If you want to write the molar, you can, but you do not have to. Okay. Is there any other information given to us in the question? Yeah, we've got the equilibrium concentration of NO. We've got 0.66 moles. And again, that's in a 1 liter flask, and that's at equilibrium. So we're going to fill that one in. The NO is 0.66. We actually know 2 other values in this table. Yes? Yeah, these 2 guys have to be 0 because what did we put into the flask? We put NOCl into the flask. It doesn't say we put in any NO. It didn't say we put in any Cl2. And so that means that if they don't mention it, putting something in, then it is at 0. And by having that 0, that allows us to find one of the changes. So what is the change in concentration of NO? Plus 0.66. And remember, the changes, the shift is proportional to the coefficients. So we've got a 2 here and a 2 here, and there's a 1 in front of the Cl2. Now, because we are making one of the products, are we making the other product or using it up? We have to be making it. If you're making one product, you've got to be making both products, right? You can't just make one of them. So Cl2 has to go up. By how much does it go up? 0.33, half as much. NOCl is not a product, it is a reactant. So is it going up or down? It's going down. And by how much does it go down? 0.66. So we do our math then to get the rest of it. 2 minus 0.66 is 1.34. 0 plus 0.33 is 0.33. And now we have equilibrium concentrations, and we are asked to calculate the KEQ. So we have used our new tool, the rice table. What tool should we use now to calculate KEQ? The KEQ expression. So you're going to write the KEQ expression. And then all you do is plug in the numbers. And we get 0.080, 2 sig figs. Straightforward enough? Okay, so we're going to do another example, quite similar to this one. Oh, but before we do, I'm going to point out to you that a rice table is the accepted method of showing work for these situations where you have initial and equilibrium. So any situation where you have initial and equilibrium conditions, you should be showing a rice table. I will take off marks if you don't show it, and as will AP. Okay, so writing the rice table is worth 1 to 2 marks in every question. And if your question is out of 4, that's up to 50% of your marks, right? So that's a lot. So if you don't show your rice table, you might only get a 2 out of 4, even if you get the right answer at the end. Okay, so make sure you show it. All right. In the last question, it started with the word initially. So we knew that we had an initial, but here it doesn't. It says 4 moles of ICl are placed in a 1 liter flask and allowed to come to equilibrium. It is found that the equilibrium mixture contains 106.5 grams of Cl2. Calculate the KEQ. How do we know that we are not yet at equilibrium? Sorry, John? It says allowed to come to equilibrium. Okay, that is what tells us we are not at equilibrium. And if we are not at equilibrium, what tool do we need to use? A rice table. You can also tell you're not at equilibrium because how many things were placed in the flask? 1 thing. And if there's only 1 thing in the flask, is there any possible way you could be at equilibrium? No. Okay. There's no guarantee if I gave you some of each that you would be at equilibrium, but certainly if you've only got 1 thing, you're not. Now, to simplify our rice table a little bit, you can put square brackets around the I and the C and the E in order to show that those are concentrations. That just makes it a bit shorter. Drawing the lines is optional, but I like them. And I'm going to let you guys try this one. Okay? One thing, if you do show the calculation for your Cl2, you should note that you are calculating the equilibrium concentration, not the initial concentration, okay? So put a little EQ down at the bottom. Did I get it right? Yeah? Cool. Excellent. Make sure, check to see, did you write KEQ? Did you write this bit here? Did you show plugging in the numbers? Did you put a box around your final answer just to be kind to whoever's marking your paper? Okay, all of those things are just good practice. Yes. That's okay because that is like this part here, right? Because it is such a simple calculation, you're just dividing by 1, that's okay. If it gets more complicated, I would suggest showing it. Do you know what I mean? Like if you were dividing by 5 or something instead of 1, then I would show it. But yeah, you don't really have to if you're just dividing by 1. All right, very good. Anytime you have only reactants or only products, you know that you are not yet at equilibrium. And if you are not yet at equilibrium, what should you be using? A race table. If you see the words allowed to come to equilibrium or allowed to react, then you know you are not yet at equilibrium and you know you should use rice. Anytime a system is not yet at equilibrium, you know you are dealing with an initial going to an equilibrium, and you will need to use a rice table. So read this next question and tell me if this is a not yet at equilibrium question, and how can you tell? How do we know? Are we at equilibrium? Nope. Because and this is allowed to come to equilibrium. Do you guys want to go ahead and try this one? Or at least get started on it? Do you need a book, David? You have one? Okay. I've written the molar because I just forgot not to. It's fine to write the molar, you just don't have to. One thing I would suggest is that although it is not totally required, if you write in your states, if you happen to have a solid or a liquid, you are more likely to remember if you write it down that you don't need to use it in your KEQ expression, okay? Here we've got gases, but uh-oh. Houston, we have a problem. I don't have any equilibrium concentrations. Whatever shall I do? I'm going to use KEQ, definitely. To calculate. Yeah. So how could I show my unknown value? You could use a question mark, or if you were in math class, what would you use? You would use an X. We're going to use an X because we've already done that when we were looking at the graphs, right? Which way does this equilibrium have to shift? It has to shift to the right. So this is going to go up. These are going to go down. All right. And anytime you have a coefficient of 1, that's going to go up or down by X. Okay. And anytime you have a coefficient of 2, that's going to go up or down by 2x. If you had a 3, it would be a 3x. All right. And that is going to allow you to write your equilibrium concentrations in terms of X. Tool number 1, race table. Tool number 2, KEQ expression. Ooh, I shouldn't have done this here. I should have done it on the line below because I want my KEQ there. Hang on. That was 4.51 times 10 to the minus 3. Okay. 4.51 times 10 to the minus 3. Then you can kind of follow along with where things go. 2x. Uh-oh. Pardon me? This looks like a quadratic equation to me. Oh. But isn't it fortunate that in Chemistry 12, you will never be required to do a quadratic equation? Never. Is there a cheat we can use, a little shortcut we can use so we don't have to do? Yes, we can take the square root of the whole thing. So anything you are given in regular Chem 12, you will be able to do just by taking a square root. Later on, there's going to be situations where you can't do that, but you can make some assumptions, which allows you to get rid of the x term, which just makes it easier, okay? But for now, you can just take the square root of everything. And if you go out of order, like if I'm like, this is step 1, this is step 2, and my step 3 is moving up here, I'm going to show that I am now moving up here. I'm going to show all the algebra here, but you don't necessarily have to show all the algebra. Oops. Oh my gosh, my grade 9s, we had a sigmoidal curve, and they just lost it. I'm like, oh my God, people are so weird. That's okay. And I was asked on the AP exam, will you have access to Desmos? And the answer is yes. Three sig figs, I think. Let's double check. 3 sig figs, 3 sig figs, 3 sig figs, yes. And at this point, I always like to go back and say, did I actually answer the question? Because I've done a lot of work, and sometimes the question asked me for something else, like a concentration, and then I'd be like, oh, have I answered the concentration? So I go, all right, what was I asked for? I was asked for the equilibrium concentration of NO. Uh-oh. So I'd better find that. So the concentration of NO at equilibrium is equal to, and then I go back up to my rice table and I say, concentration of NO at equilibrium is equal to 2x. So that's equal to 2 times 0.03 249, which is equal to 0.06497, which would round to 0.0650. And we are dealing with a concentration, so what else do we need? We need molar. I think I forgot to do that in the other block. Uh-oh. I'd better post this one. Okay, so always go back and check, what am I solving for? Does it need a unit? Did I need to multiply by 2? Okay, always go back and check. Then there's some exercises, which we're not going to do right now. We're going to continue on, and we are going to virtually finish all the KEQ stuff today. We have one tiny little extra thing, because there's not much to it, right? Once you know how to use rice, and now you're going to learn how to use Q. And the only other part is if you know that KEQ is greater than 1 or less than 1, whether it favors reactants or products, and we've already sort of talked about that, we're virtually done with KEQ. So your quiz on 2.3 and 2.4, which is entropy, enthalpy, and spontaneity, which we will also cover like on Monday, okay, is going to be Wednesday, October the 8th. We will be done the unit at that point, but your test will not be until Wednesday, October the 15th, okay, so that you have lots of time to study, et cetera, because apparently on the Thursday, there's like, I don't know if you guys have 2 tests, but a bunch of people in my morning block have 2 tests on Thursday. I want to make sure I get your quiz back to you and you get a chance to review. I want you to make sure you have a chance to ask me questions after the weekend, right? So that would be on the Tuesday, so our test will be on the Wednesday. In the meantime, we will be doing some AP stuff, which will not be on the test, and we might start Unit 4. I know, you're like, what happened to Unit 3? I really need to renumber the units, but I have not. It requires a lot of fussing around to change all the numbers in every workbook. So, and I've only got 5 years left of teaching, and you guys are grade 12, so next year's grade 11. I've only got 2 more years of teaching grade 12. So I'm like, do I really bother? Nah, I'm like, eh. So we're doing Unit 4 before Unit 3. Okay, I like how it works better when we do that. Plus, it gives you the 3 easiest tests right at the beginning. So when you submit your marks to universities, guess what? It boosts you. Yeah? So it's kind of nice. All right. So far we've only dealt with situations not at equilibrium where we have only reactants or only products. But now we're going to have situations where we toss some reactants and some products into a container. Is there any guarantee if I have some reactant and some product that I am at equilibrium? No, there's no guarantee. I might have too much product, I might have too much reactant, and that is where Q, pen seems to have died. Let's fix that. That's where Q comes in handy. So this is a situation where you are given concentration of both reactants and products. We don't have a side that is 0 molar, so we don't know which way it is going to shift, right? We don't know if we're too far to the right or too far to the left. So we are going to use the reaction quotient, Q for quotient, to tell us which way the equilibrium shifts. And Q is exactly the same as KEQ. The only thing that is different is that KEQ uses equilibrium concentrations and Q uses initial concentrations. So when you write the Q, I do suggest that you write little I's in there. You don't have to write it for the KEQ because everyone knows what that is. But when you write the Q, do write the little I's in there to remind both yourself and whoever's marking it that you are putting in initial concentrations. Q can also be called K trial because you're trying out values in the K expression. Okay, or trial KEQ, because again, you're trying out values in the KEQ expression to say, am I at equilibrium? If not, am I too far to the left or am I too far to the right? I tend to use Q because number one, it's really short and therefore efficient to write, but also it's not a constant value. It could be anything depending on what your initial concentrations are. So I like that it doesn't have a K in it. Are you guys familiar with the story of Goldilocks? Has anyone not heard the story of Goldilocks? Goldilocks and the Three Bears? Have you never heard it? That's okay. That's okay. Because I took time in the other class to share the story of Goldilocks. Would you like to hear the story of Goldilocks? Okay. You guys can tell me if I do a good job or not. I did it this morning, so I kind of remembered where I was going. So anyway, there's these three bears, and they live in a cottage in the woods. There's a mama bear, there's a papa bear, a daddy bear, and a little bitty baby bear. And they live in this cottage in the woods, and one morning, they make porridge for breakfast. Porridge is like oatmeal or congee or something like that kind of a thing. Okay? So, they make this and it's too hot to eat. So they say, oh, while we are waiting for our porridge to cool, let's go for a walk. So they close up the house and off they go for their walk. Well, down the pathway, skipping towards their cottage, after they've left, comes a little blonde-haired girl named Goldilocks. And I don't know what's wrong with Goldilocks. Seems like she's got like antisocial personality disorder or something, but it's called conduct disorder when they're younger, right? Because she seems to keep committing these crimes. So she just opens the door to this cottage, right? And walks right in. Like I said, conduct disorder. That's not something normal kids would do, right? So anyway, in she goes, and she goes in, and oh, there's the living room. And she's like, oh, a chair to sit down in. I've been walking for a long time. So there's 3 chairs. She sits down in the first chair and she's like, oh, this chair is too hard. And then she sits down in the next chair, which is Mama Bear's chair. So the first one was Papa Bear's. Next one, oh, this chair is too soft. And then she sits down in the third chair and she says, oh, this Baby Bear's chair. She says, oh, this is just right. But she's maybe been eating too much porridge because she breaks the chair. And now she's like, oh, no. But in the meantime, she's gotten a little hungry. And she's like, well, I guess we'll just leave that chair there. And she smells something delicious from the other room. And so she goes in there, and there on the table are 3 bowls of porridge. And she goes, oh, this looks great. So she tries some of the first bowl, and she's like, oh, this porridge is too hot. Ah. And then she tries the next one. Bleh, bleh. This porridge is too cold. And then she tries the last porridge and she says, oh, this porridge is just right. And she eats it all up. And then, having a little, carb crash, she starts to feel pretty tired. So she goes looking to see if there's somewhere to lie down. So up she goes, up the stairs, and she gets to the top of the stairs, and there's 3 beds. And she lies down in the first bed, Papa Bear's bed, and she says, this bed is too hard. And then she lies down in the second bed, Mama Bear's bed, and she says, oh, this bed is too soft. And then she lies down in Baby Bear's bed, and she's like, oh, this bed is just right. And she falls fast asleep. In the meantime, home come the bears. Home come the bears. And they walk in and they look at their living room, and Papa Bear sees a dent in his cushion in his chair, and he says, "Hey, someone's been sitting in my chair." And then Mama Bear sees her chair with a dent in the cushion, and she says, "Someone's been sitting in my chair." And then Baby Bear sees his chair, which is all broken, and he says, "Someone's been sitting in my chair, and they broke it all to pieces." And then they're like, "What else is going on in this house?" So they go to the kitchen. And they see the bowls of porridge, and they see they've been disturbed, and Papa Bear says, "Someone's been eating my porridge." And then Mama Bear says, "Someone's been eating my porridge." And Baby Bear says, "Someone's been eating my porridge," and they ate it all up. And then they're like, "What on earth is going on? Let's go see how things are going on upstairs." And they go up the stairs, and they see the bed linens have been rustled all around, and the Papa Bear says, "Somebody's been sleeping in my bed." And Mama Bear says, "Somebody's been sleeping in my bed." And then the Baby Bear says, "Somebody's been sleeping in my bed." And she is. And at this point, Goldilocks wakes up. She sees the three bears. She has a panic attack, and she runs down the stairs and out. And her life of crime is stopped because she was too terrified of waking up to see bears again. Thank goodness we protected the world from another sociopath. All right. And that is the story of Goldilocks and the three bears. And the moral of the story is that we have the thing that is too such and such, too big, too small, just right. And Q is the Goldilocks of equilibrium, because what we do is we take our value of Q that we calculate using our initial values, and we say, if our Q value is bigger than KEQ, that means that Q is too big. And what is Q? Q is the product over the reactants. And if Q is too big, what do we have too much of? We have too much product. So Q is too big. So in other words, we have too much product. Yes. Yeah. So if the product is too big, then the system needs to shift to the left to produce more reactant and use up product. Until the ratio of products to reactants equals KEQ. Now, if Q is smaller than KEQ, in other words, if Q is too small, that means that our ratio of products to reactants is too small. And if it's too small, we have not enough product, right? And I tend to think in terms of product because it's the one that's on top, so it's easy for me to see, oh, I need more product, or I know I need less product. But of course, the reverse thing is always going to happen to the reactant. So the system is going to shift to the right to produce more product until the ratio of product to reactant equals KEQ. And if Q is equal to KEQ, that means the ratio of products to reactants is just right. And therefore, the system is already at equilibrium. And it does not shift. Okay, so what we're going to do is we're going to look at a couple questions that use this just to predict the shift. And then we're going to use it in a question where we need to do some actual math after we predict the shift. And then we're going to be done. Hooray. Okay. So here we have a question. We start with 4 molar CH4. We start with 2 molar C2H2, and we start with 3 molar H2. In which direction will the reaction progress to reach equilibrium? So if you're asked in which direction will the reaction progress, that tells you in your toolkit to go and take out Q. Okay? So you're going to write the Q expression just like you did a KEQ expression. And I'm going to go back and put my little I's there for initial. Honestly, I don't think if you don't write them, anybody's going to get mad at you, but I don't know that for sure. So I would hate to say that and then it matters, you know? Hey. Question. Do sig figs matter here? Well, what is the question asking you? In which direction does the reaction shift? Unless they are like so close, it really doesn't matter. But what you do have to say is once you've got your, you get a mark for writing Q, you get a mark for writing that, you get a mark for writing that, you get a mark for getting the correct value or whatever. And then you would have to say Q, which is 3.375, is greater than KEQ, which is 0.154. That's given to us in the question is the KEQ. And then you do not need to write this part, but I find it just helps my brain because, like I said last day, I don't have that good of working memory, right? So I'm going to be like, okay, products over reactants is too big. Therefore, shift towards reactants. In other words, to the left. Okay? And so then over here, I would just write, therefore, the system shifts left. Yes.
Is it okay to use the therefore song?
Yes, therefore is well known and used
I think.
in AP and everything. Yes. Therefore symbol is totally good. Would you guys like to try example 2? I would say because we've got a 5-liter flask here, probably show your calculation of concentrations. Oops. Oh, that's okay. Ah! Jumping around on me. Did you guys get 1.12 times 10 to the minus 3? Okay. Yes. I would. And the reason I would is because I have to mark these things. And so it makes it easier if I can see what the numbers are without having to look myself. Do you know what I mean? Whoops. So yes, please write these numbers. Yes. It would be 2 sig figs, but I don't really care that much. Because in this particular equation question, all I'm asked is in which direction it shifts. So I could write 0.0011 and that would be fine, but it gives me the same result at the end regardless. And like I said, you don't need to write this little part, but I'm like Q, which is the products over the reactants, is too small. So I need to shift towards products, which is to the right. But feel free, if you want to write that anyway, like there's no harm in just putting it in with the main body of your answer, okay? What you making, Victoria? It looks exciting. It's got like little like holes in it and stuff, like, ooh, fancy. Nice. All right. And now we have a big bad question on the next page. So I want you to read the question and decide what tools will you need from your toolkit to solve this question. So what are our choices of tools? Rice, Q, KEQ. Do we need a rice table? Yeah, we do, because we're asked, when equilibrium is established. Okay, so we know we need to use a rice table. Do we need to use a Q? Q tells us which direction it shifts. Yes, because we are given both reactant and product. And I'm just going to quickly write the first couple lines of the rice table because I'll show you a common mistake that people make. Okay, so there's our reaction. SO3 plus NO, SO2 plus NO2 gas. And here is where people will make the most common mistake. And that is they will look at this and they'll say, I have more reactant, 0.5, than I have product, 0.3. Therefore, it must shift to the right. Is that a correct statement? No, you can't know which way it's going to shift unless you know how much you have compared to what your actual ratio should be. And in fact, for this one, our KEQ is 0.015, which is less than 1. And if it's less than 1, what does that tell us about the equilibrium? It favors the reactants quite significantly, yes? So in our rice table, we can say, oh, the reactants are favored, but are they favored enough? Are they favored too much? How can you tell? What would you need to use? You would need to use your Q. And once you've got, whether it's shifting left or right, that allows you to put your pluses and minuses in the right places in the change. In this case, it is shifting left. So you should have pluses on the left side of your table and minuses on the right or product side of the table. What numbers do we put in there? X. Oh, and everything's got a coefficient of 1. Isn't that nice? And it's up to you whether you write your KEQ as 1.5 times 10 to the minus 2 or 0.015. I kind of like 0.015 just because it requires less writing, but it's totally up to you. Oh no. Do I need to solve a quadratic? No. Because in Chem 12, we'll always give you something, at least in this unit, where you can take the square root. Uh-oh. I do this all the time. It's 0.5 plus x, plus x, plus x. There we go. Yikes. Did you guys get the same answer as me? Like if you, yeah? Okay, good. Is this the actual answer we want? No, because once again, I've just solved for x, and then I need to go back and go, what was I actually being looked for? The equilibrium concentration of SO2, which is 0.30 minus x. And then what should we be asking ourselves at this point? We need to have molar, and we need to have sig fig. So is my correct answer 0.087, or is it 0.09? (0.09), because remember, when you're subtracting, you find your first uncertain digit, which is, in this case, is in the second decimal place. There's our second decimal place there. So that is going to become 0.09, and then we can put our molar and be done with that. So that's quite a lot of work, yes? For one question? Yeah. That's as bad as it gets in this unit. Okay, there are no calculations that are worse than that. Yes?
0.125.
Yes.
121.
Here?
There
And here. That's because, oh no, that's okay, because what I've done here is I have added this x onto that. Yeah. So that gives us that there. And apparently Desmos, which I have never used, has some like magic algebra thing. Is that correct? Desmos? No? Okay. Everyone was so excited this morning when they learned they got to use Desmos on the AP exam. I don't know. I just do algebra the way I've always learned it. Yes?
Use Desmos, so it basis solvent iteration. How do you show your work?
Well, this is what I don't know. I don't think you don't need to show every single step of the algebra, but yeah, you won't get to use Desmos on your regular test anyway. So yeah.
Yeah, isn't it easy that most of the voice, but the written is written?
Written is like you have to write the answer. Yeah, the question is on the screen, but you have to write on the book.
But you still have the screen, so you can do whatever you want with the screen.
So I'm assuming you can use Desmos if you want to. I don't know. Life has become so much more complicated since it was all on, like, you know, everything changes every year. The first year, they were like, oh, they put the periodic table on the screen rather than giving you a hard copy and the formula table. And so they did that for one exam. And then in between that first exam and the other exams that had like data tables, they were like, oh, that's a bad idea. And like any teacher could have told you that was a bad idea. Why did you not just ask literally anyone? Anyway, so that now you get a hard copy of the periodic table and a hard copy of the data books. Yeah. So. Yeah. Anywho, that is it for today. Your homework is pages 92 and 95. That's 7 questions altogether, so it's not too bad. Okay. And that's as far as I got with my other block because I was left with 9 students by the end because everyone went to Clubs Day to set up. And I only started with 22 people and 2 were away. 22 people, 2 were away, and then 11 went to Clubs Day, so I was left with 9. So there we are. Yeah.